This lecture, I'd like to discuss some scaling laws. Now, what are scaling laws? Well, we all have an idea of how big forces or effects might be at the macro scale based on our exploration of introductory physics and some other associated classes. But how does the strength of those effects or the magnitude of those effects change as you start to scale down the size of your objects from the macro scale objects on the order of a meter, for example, down to the nanoscale, 10 to the minus 9 meters. So the effects, in order to get those in our heads and cement those ideas, your textbook, which is, of course, Nanotechnology Understanding Small Systems, your textbook explores different scaling laws, okay? So the first one of those scaling laws that I want to deal with are some of the ones from mechanics, all right? So briefly to remind you, in a previous lecture, we explored this idea of the surface area to volume ratio. And we explained why a high surface area to volume ratio led to a larger amount of chemical reactivity. Okay, so we talked about that already. Now, regardless of the shape of the material, you can think of a material or an object as having a characteristic dimension to it. So for example, if you wanted to talk about a person, maybe the characteristic dimension for the person might be that person's height, which would be, you know, a couple of meters, right? On the order of a couple of meters. I'm shorter than that, but still, okay? So that would be the characteristic dimension for a person. The characteristic dimension for a fork might be about 10 centimeters or so, okay? So we're talking here sort of back of the envelope calculation, just round numbers. And then what we're going to do is talk about how changing the size of that characteristic dimension, which we call capital D here, right? How changing the size of that characteristic dimension affects the material as you go for different phenomena, all right? Okay, so for example, surface area to volume ratio. Our characteristic dimension, which we call D, for the surface area, that would be proportional to D squared. Now, for different shapes, you're going to have different formulae for surface area, but all of them are going to go as the characteristic dimension squared, if that makes sense. So this approach is very much from a back-of-the-envelope calculation kind of approach. We're not looking for the exact ratio here. We're just trying to scale it inside of our heads. I hope that makes sense. Now, the surface area would go as D squared, but the volume, right, would go as D cubed. Okay, yet again, I don't care like what the exact formula is at this point. So for a cube, it might be D times D times D, and it really would be D cubed. But for a sphere, it would be 4/3 pi D cubed, and D would be the radius of the object, okay? So I just care that it's proportional to that characteristic dimension, whatever you pick for the particular phenomena you're trying to explain, that characteristic dimension cubed here, for example. So that means that our surface area to volume ratio, the scaling law for that would be 1 over D. Okay, so this is one we've already explored, and I hope that makes sense to you. Let's look at some other scaling laws. Okay, so first I want to explore some scaling laws for mechanics, right? It's the first physics subject that everybody encounters, right? Mechanics, so let's go over that one first. So bear in mind that all of the scaling laws that I'm getting ready to tell you about now should be taken with not just a grain, but a huge block of salt. They're meant to guide your thinking, but it's not meant to give a precise measurement of anything here. Okay, so they're going to scale as, in other words. So you should think of it like a back-of-the-envelope calculation yet again. So let's do strength to weight ratio. This is everybody's favorite. Okay, here we go. Strength to weight ratios. So one property that's affected by the characteristic dimension and how it changes, the surface area to volume ratio is changing, is your strength to weight ratio. Now your text goes through this from a biological standpoint, but I'm going to look at it from a materials scientist standpoint because, you know, condensed matter physicist, that's my background, so I like that one. So I'm going to approach it from that direction, and your text approaches it from a different direction, okay? You should read the text though. Okay, so speaking of material science, material scientists use what's known as the stress-strain equation for describing the strength of materials. So here, the stress, which is symbolized by the Greek letter sigma, is equal to the force divided by the cross-sectional area of the material, okay? So, for example, if I'm tugging on this fork, right, I'm tugging this way, I'm applying a force along the axis of the fork, right, and then I'm pulling with a certain force, but it would be harder to stretch out a thicker, fatter fork than it would be a tiny little skinny fork. So that's why the area appears in the equation, the force divided by the area. It normalizes it out so that you're just looking at the material properties, okay? So here we have the force divided by the cross-sectional area. That's our stress, right? And it's equal to what's known as the strain, symbolized by the Greek letter epsilon, times the quantity known as the Young's modulus of the material. Young's modulus or elastic modulus, symbolized here by a capital letter E. Now the strain is how much the object stretches when you tug on it, right, delta L, divided by its initial length. Okay, so the strain epsilon is equal to delta L over L, how much it changes in length divided by its initial length. The Young's modulus is considered to be a material property. So for example, the Young's modulus for steel will be much greater than the Young's modulus for plastic, for example, okay? Because the steel is a lot more resistive and changes length less when you pull on it, right, compared to plastic. Okay, so this Young's modulus is something that you can look up in different tables, and it changes from material to material. Now, people are used to thinking of a Young's modulus as a constant, and it kind of is, but what happens is, if you were to tug on 100 different pieces of steel, right, and try and pull them apart, you'd get a different measurement of the Young's modulus for each one of those pieces of steel, all right? And then the one that gets reported in the literature is the average of those, all right? Now, the reason for this is, of course, because every material has defects in it, and different materials will have different numbers of defects in them. And so the defects are, usually the breakage starts at the defects and changes with the defects, and so it's proportional to that. All right, now, when you're talking about the strength of a material, the Young's modulus definitely factors into it. But what your text does is talk about strength in terms of the amount of force that that object can support or hold or withstand, okay? So what we would do is in the equation for stress strain, we would back out the force by multiplying both sides by the cross-sectional area of the material. So the force would be equal to the cross-sectional area times the Young's modulus times the strain, okay? Now, if we assume that the Young's modulus is a constant, right, and then the strain is something that's set, right, also the strain, remember, is a change in length divided by a length, so it's dimensionless, and then we treat the Young's modulus like a material constant, then what that means is the force which that object can support, withstand, or hold is proportional to the cross-sectional area A. So that means that the force, the strength, is proportional to the characteristic dimension d squared. Okay? Hope that's clear. If not, pause it and make sure to go back over that argument in your head. But for now, remember that the force, the strength of the material, is proportional to d squared. Okay, so it's a strength to weight. We've got the strength part, that's proportional to d squared. Now we've got to talk about the weight part. Okay. Well, from introductory physics, the equation for the weight is the mass of the object times the acceleration due to gravity here on planet Earth, which is 9.8 meters per second squared. Of course, that acceleration here on planet Earth, we're going to treat that as a constant. So we back that out. We don't consider that in our scaling law. That means that the weight is going to be proportional to the mass of the object. Okay? Well, the mass of the object is proportional to how big it is, right? The way that we count that up is we say that the mass is proportional to the density of the object, which we're going to treat like a constant, right? The density of the object is a known constant, times the volume, okay? Now the volume is proportional to d cubed, the characteristic dimension cubed. So that means that our weight part of the thing is proportional to d cubed. So the strength to weight ratio is going to be the strength divided by the weight. So we have the scaling law for the strength, which is d squared, and we're going to divide it by the scaling law for the weight, which is d cubed. So the strength to weight ratio scaling law is going to be 1 over d. Okay? So whatever your strength to weight is for a particular object, that will then scale as 1 over d. So as an example of this, let's think about the elephant and the flea. Okay? So an African bush elephant, it has an average mass of about 6,000 kilograms. It's about 4 or 5 meters tall. A flea has a mass of about 1 milligram and a size of about 2 millimeters. Okay, so if you measure the length of a flea, for example, it's about 2 millimeters. So we're going to take the characteristic dimension of an African bush elephant as 4 meters, and we're going to take the characteristic dimension of a flea as 2 millimeters. So those are our D's for the elephant and for the flea. That means that the strength to the weight ratio, if you were to compare the scaling of the strength to weight ratio for an elephant and the strength to weight ratio of a flea, it would be about 1/4 inverse meters, right? 1 over d, d is equal to 4. So 1 over 4 is 0.25 inverse meters for an elephant. And it would be about 1 over 2 millimeters, or 1 over 0.002 meters, which is 500 inverse meters for the flea. So you can see here that the strength to weight ratio scaling law for a flea is 2,000 times that of an elephant, right? So if you scale it, a flea is 2,000 times stronger compared to its weight than an elephant. Now you're thinking, that's stupid. I have never in my life seen a flea carry a person on its back, but I've seen that lots of times for elephants. That's not what I'm saying. I'm not saying that they can lift more raw weight. What I'm saying, though, is that for their size, they are way stronger. An example of this is that a flea can jump about a foot, right? It can jump an amazing distance, hundreds of times its body length in some cases, right? However, an elephant can't jump at all. You'll never see an elephant jump. They kind of plod along, and then occasionally they trot. But jumping? No, not something an elephant can do. Okay? They can't do that because they weigh so much, all right? They're so big. So you can throw a flea out a 2-story window. The flea will be fine. An elephant, not so much, okay? It won't be able to land and support its weight. So the strength to weight ratio of the flea is a lot greater than that of the elephant. Here's another example, okay? So this one gets a little more quantitative. Based on the scaling laws, how many times greater is the strength to weight ratio of a carbon nanotube, which has a characteristic dimension of, say, 10 nanometers, than the leg of a flea, which has a characteristic dimension of about 100 micrometers? And then compare that to the leg of an elephant, which has a characteristic dimension of about 2 meters. Okay? So here's the scaling laws. The strength to weight ratio of a nanotube, that's 1 over the characteristic dimension. Well, 10 nanometers is 1 times 10 to the minus 8 meters. So 1 over 10 to the minus 8 meters is 10 to the 8 inverse meters. Now, for a flea's leg, you've got a strength to weight ratio. 100 micrometers is 1 times 10 to the minus 4 meters. So 1 over 10 to the minus 4 gives you 10 to the 4th inverse meters. So what that means is that the nanotube scales is 10 to the 4th times greater than the flea, right? The flea leg. Now, how about compared to the leg of an elephant? Okay, the characteristic dimension there is 2 meters. So the strength to weight there for an elephant, the scaling law, would be 1 over 2 meters. 1 over 2 is 0.5 inverse meters. So that means that compared to a carbon nanotube, right, it's much, much weaker. The carbon nanotube is 5 times 10 to the 7th, right, stronger for its size than the elephant is. Okay? I hope that cements it in there. Now, there's some other mechanics scaling laws that I'd like to briefly cover in a little bit less depth, since you kind of got the gist of what I mean now. But let's talk about friction, for example. This is a good one. So on the nanoscale, friction, even forces that you might ignore, like weak van der Waals forces or capillary forces, friction at the nanoscale and the microscale can really seize up some of those nanoscale and microscale little engines and moving parts. Okay, so stuff that you would ignore at the macroscale can completely dominate when you start shrinking things down. Now, part of that reason is that the law of friction that we have on the macro scale doesn't really work so well when we shrink it down to the nanoscale. So here we go. On the macro scale, the equation that you're used to from your introductory physics textbook is Monton's law, which says that the frictional force is equal to, in magnitude, the frictional coefficient, which we call mu, times the normal force, right, which we call big N here, all right? So the frictional coefficient is often treated in introductory physics textbooks like some constant that you can look up. So they'll give you, say, for example, oh, the frictional coefficient for an ice and a sneaker is 0.01 or something, and you'll, dutifully write it down on your physics homework. But the truth is a lot murkier than that, and these frictional coefficients can vary a lot depending on conditions. So one of the reasons for that is that Monton's law tells us that friction is independent of contact area. In other words, there's nothing in that equation that has to do with contact area. The frictional force is equal to some coefficient, which is a material property, right, times the normal force, which is, how strongly those two things push on each other, right? But the deal is that if you zoom in from a macro scale view of the object into a nano or micro scale view of the object, then what happens is that the apparent contact area and the true contact area are not the same thing, okay? So if you look at any object, for example, under a scanning probe microscope, and you look at what the topography of that object is, most objects look like puffy clouds, okay? You see these bumps and valleys and hills and valleys, and that's what almost every object in the world looks like under a scanning probe microscope. Sometimes instead of gentle rolling hills, you get spikes, but still, puffy clouds and mountain ranges, that's what it looks like. So what happens when you push two objects together is that the objects touch one another at the tops of the bumps. Okay, and these bumps we call asperities. Okay, so the objects touch at the bumps or the asperities, and then the greater the load, the harder they push together, the larger the normal force, the more those objects mush together, and the greater the true contact area. So we call the true contact area how much they actually touch. So for example, the apparent contact area of this book on the table is the area of the book, but the true contact area is going to increase the harder I push the book into the table, because the bumps are going to mush out and they're going to touch more, okay? So on the nanoscale and the microscale, the frictional force is actually proportional to the contact area, which would mean that it's proportional to d squared, okay? So that's the scaling law that you might want to think about for friction. Now, people often think of friction and wear together because, of course, the rubbing of objects together does cause one part to wear away, for example. Okay? So wear is proportional to how thick the part is, right? So everybody's probably dealt with tires before, and you watch your tire tread wear down as time goes on. And then you figure out when to change your tire by how worn away the tread is. So the thicker the tread, right, the thicker the tread, then the longer the life of the tire, right? So that's a very akin to the idea that I'm trying to get across here. Let's say that you have some sort of sacrificial coating that you've put on a part, like a plating or something on a metal part, and you want that coating to protect the part underneath. Well, how long that lasts is going to be proportional to how thick your coating is. So that means that the wear is going to be proportional to D, right? How thick your coating is. So wear is proportional to D. One last one that I want to cover in mechanics is springs, okay? So let's think about taking ourselves back to introductory physics once again, and the equation which governs springs is Hooke's law. The magnitude of the force that the spring can exert is equal to the spring constant, K, which we'll treat as a constant, right, times the amount that spring is stretched, which we'll call X, okay? So if the spring constant, we think of that as a constant, then X is going to be how much that spring is stretched, and that's going to be the dimension. So that means our spring force is going to scale as D, right? So maybe it scales as the length of the spring itself, all right? So spring force scales as D. Now, how about the frequency of oscillation of that spring? So let's say that we suspend some object from a spring and we let it oscillate back and forth, right? How would the frequency of that oscillation scale? Well, the frequency of oscillation is going to be proportional to the square root of our spring constant, which we're treating as a constant, divided by the mass that we're attaching, right? So it's going to be proportional to root k over m. Now, since the mass scales, we've already talked about how mass scales as the density times the volume, right? And so that means that the mass is going to scale as d cubed. So that means that the frequency of oscillation is going to scale as d to the minus 3 halves power, right? Okay, so that has many applications in different forms of imaging, such as my personal favorite, atomic force microscopy, which uses a cantilever right here, as you can see, with a sharp tip on the end, which raster scans over a surface. Now that cantilever has an oscillation frequency, okay? And that oscillation frequency is going to scale as d to the minus 3 halves. Okay, that's probably enough for today. In our next lecture, we're going to get into some scaling laws for electricity and magnetism, and we'll pick up there. Thanks.